Right now, I'm working in Aker Solutions with focus on numerical simulations and model test of Arctic structures. First, I would like to introduce some basic information on our model test and briefly introduce ice model test setup. Of course, in the model test, we found some very interesting phenomena and observations. I think they're very important to the Arctic structure design, especially for the station keeping structures. Finally, I will make some conclusions. This model test was done in the ice basins of Marine Technology Group in Aalto University. The tank is very big with dimension of 40 by 40 by 2.8. The scope is to observe ice breaking and ice accumulation, measure the dimension of broken ice flows, measure the ice force. Before we did this model test, we have already developed our numerical models. So this model test is also used to validate and modify our numerical models. The ship models I used is MT Uikku. It's an ice-breaking tanker. The scale is 31.6. The dimension is shown here, and the ship has a length of 150, 21 in breadth, 9.5 in depth. In addition, at the middle of the hull, this slope is not vertically. It's about 82 degrees. Model test setup. In the model test, this ship model was connected to the carriage by this up frame and a very steep tube. We use 6 degrees component load transducer here and one directional load cell here. We also used a dynamic measurement unit to measure the accelerations of the ship. Two cameras are used. One is above the water in front of the bow, trying to observe the ice breaking process, and another camera was installed on the water to observe ice accumulation phenomena. In total, we have done 11 tests with different ice drifting speed and headings. The ice drift speeds are very relatively low because low speed are very important to the station keeping of the Arctic structures. The speed used 0.2 and 0.5. I used the 3 heading angles here, 0, 45, and 90. The measured parameters include ice force, accelerations, the dimension of ice pipe, and the size of ice flows. For the 0 degree cases, we have 4 tests. The ship was fixed and the ice is moving towards this ship, but in the model test, the ice was stationary, and actually the ship models was towed towards the ice field. Then we come to some observations for these zero heading cases. We find that ice are often filled in the bending at the bow area. The circumferential creeks occurs first, followed by radial creeks. Sometimes we can also observe this rebreaking at the shoulder area, and of course this broken ice wake was not symmetric at the port and starboard. When the ice was submerged down, and it could be possible that the ice flows was cast laterally. You can see from these pictures here that a lot of ice flows was cast, and there's no ice accumulations under the hull according to the videos. Then we come to the 90 heading cases. The ice is coming sideways to the hull directly, so this case represents the extreme conditions, the most extreme conditions. There are also 4 tests in the 90 heading cases, and ice mainly filled on in the crushing and mixed structures moved at the mid hull, but at the bow and the stern, the ice bend. The most interesting things here is that ice drift speed significantly affected the ice accumulation phenomena. At the low speed, you can see there's a lot of ice flows accumulated on the level ice on the on the upstream of the ship, while if at the high speed in this finger there's the most no ice accumulations. So here I would like to show the 2 videos on this phenomenon. The first video is for the low speed. This is the bottom of the hull, and this hull is moving towards the ice. The videos was made from on the water. So you can see ice accumulation. Ice pipes was accumulate. It was like rolling, but almost no ice flows just go under the hull, bottom of the hull, and to the other side. The second video is for the high speed. Here I see high speed is 0.5, but it's also very small. You can see almost all the broken ice flows went on the bottom of here and to the other side. There's no ice accumulation on the upstream. This is the end of the model test. This is very important to the ship design. I will come to that later. Yeah. 45 heading cases. There are two cases here with heading 45 degrees, and ice accumulation also occurs regardless of the ice drift speed. The amount of the ice pipe increased from the middle hole to the stern, and the filling modes at the different part of the hole was similar to that 90 degrees cases. As a result, for the head-on or zero heading case, and this is a vertical level is a longitudinal ice load. This is more interesting to us. This load was plotted as a function of ice drift speed. This is a text number, and you can see this ice load increased as this ice drift speed increased. For test 103 and 104. The main difference is only the ice drift speed, and for from test 205 and to 206, we also see the similar trend. For 90 degrees, it's not the same like that. Both the mean values and the maximum values tend to decrease. That's because when the ice drift speed increased, there's no ice accumulation, so that force component decreased. 45 degrees, as the ice drift speed increased, there's a slightly increase as well in the load. Conclusions: 0 degrees, no ice accumulation. For 90 degrees, ice drift speed matters. For 45, of course, for 90 degrees, the amplitude of the transverse force was very high. I remember it's about 20 meganewton in force scale. For 45 degrees, this ice filling mode is very similar to a 90 degree case, and the force level was also comparable to those of the 90 heading cases. But the ice drift speed effect is very minor. If here are some references on the numerical and experimental studies. If you are interested in this topic, you can just search online. Thank you for your attention. Thank you.
Thank you. Thank you, Lee. Do we have any questions? And if you do, please introduce yourself.
You have a speaker? Okay, thank you. I'm Ove Gudmestad. I have a question. Will Aker really moor a ship up in ice under this condition? You don't have study ridges, you have just study a very small ice sheet. Isn't it a bit dangerous to present this very simple model without a long disclaimer as normal from Aker?
Actually, of course, this case is where, or say it's sudden happened in the actual. But we want to say how to say the ice crashings at the hole, at the middle of the hole. That's dominant force, I think.
Well, in my opinion, you can never do this without having an option to disconnect the vessel if the ice load is getting much higher than you calculated.
Correct, because this model is fixed in 6 degrees of freedom. It's impossible to get so high stiffness of a tube or something. Or in general, the aim of this one is just to measure the ice force. We try to compare the ice force with the simulated ice force.
Just a small comment. He did this for his PhD at NTNU, and first afterwards he joined Aker Solutions. Yeah. Okay, do we have any other questions? Yes, Mark.
Mark Rijnbreteler of the Deltaris. It's not really my topic, so perhaps this is a very stupid question, but what I saw in your test results is that you have a mean velocity here on the hull of the ship and quite large standard deviation. Still you had a very nice homogeneous ice sheet. I can imagine that in reality the ice sheet is much less homogeneous and giving even more larger standard deviation of your forces. How do you cope with that variation of forces?
Deviation of force. This value was just based on the measured values, and actually. In my numerical simulations, the parameters are fixed. So we have diminished check values. Of course, if you want to have Gaussian distribution of the ice properties, you might have a lot of data.
I can imagine that you shouldn't design on the average values, but more on the extremes.
Yes. I think it's like this data is not directly used to engineering, because this case is, for example, 90 degrees. It's no, you can't design a ship with 90 degrees and fixed at that tiny angle. Actually, we try to do it in the marine system, with the marine system, and release rotation. Yeah. And of course, when the ice comes in the sideways, this ships could remove due to its ice moment and towards to the coming ice.
Okay, thank you very much. One final short question.
Also from Wallingford. When I first came across ice modelling in the 1980s, it was done by a plastic stearate deposited on the water. But you left out at the beginning of your talk, the really important part is, how did you make the model ice? And how did you prove that your model ice behaves in any way similar to real ice?
I think that would be a presentation of its own.
I think Rudik.
Well, I can quickly explain that the model ice that we have is NFG, fine-grained model ice. We use ethanol to weaken the ice, and there have been full-scale tests compared with model-scale tests in the past that validated that, at least for ice-breaking processes, the ice is scalable. But of course, there are still many areas where the scalability might be questioned. Yeah. Right, and thank you very much, Lee.